Hello everyone, my name is Huahuang from the Hong Kong University of Science and Technology. Today, I'm glad to do the presentation of an integrated temperature compensation method for thermal expansion-based angular motion sensors. Here is the outline of the presentation, and I'm going to start with the introduction. In this part, I will show you the motivation and some background information of my research project. Also, I will briefly introduce the proposed 2D model for temperature compensation analysis. The third part is about the experimental study of the temperature-compensated thermal expansion-based angular motion sensor, including the fabrication process and experimental testing results. In the end, I will draw a conclusion. Angular motion sensor, also known as gyroscope, has become a household word because of its popular and various applications, including the inertial navigation system for aircraft, motion controlling in robotic industry, and motion sensing in consumer electronics. However, some conventional gyroscopes are still costly, bulky, and fragile. By contrast, MEMS thermal-based angular motion sensors are simpler, less costly, and compatible with CMOS process. Our research work focuses on the thermal expansion-based angular motion sensor. We call it TEAM sensor for short. Unlike some conventional MEMS gyroscopes, thermal expansion-based angular motion sensor reveals much simpler structure by replacing the solid proof mass with the fluid medium. So it is easier for the TEAM sensor to realize miniaturization and achieve higher shock resistance. Also, the TEAM sensor will be less costly since its fabrication process is compatible with CMOS process, and the mass production can be achieved. Generally, thermal expansion-based angular motion sensor consists of 2 heaters and 2 temperature detectors. The thermal gas flow is generated by alternatively heating and cooling the heaters. As shown in this video, when there is no input rotation, the thermal flow will expand symmetrically, so the temperature detectors on the left and right-hand sides will sense the same temperature. While in the presence of the rotation, the induced Coriolis force will distort the previous symmetric temperature profile. As a result, a temperature difference will be detected and then associated with the input angular rate. Currently, there are few research studies on the ambient temperature effect of the TEAM sensors, and there is no simplified model to investigate the impacts of the working fluid's thermal properties and predict the temperature drift of the TEAM sensors. By extending the previous 2D model with the consideration of the ambient temperature effects and the working fluid's thermal properties, we developed an integrated ambient temperature compensation method for TEAM sensors to effectively improve the output stability and accuracy. The temperature compensation algorithm predicted by the 2D model is adopted in the open source Arduino MCU in the experiment to compensate the sensor output, as shown in this figure. Based on the analysis in the extended 2D model, we can see that the variation of the working fluid thermal properties can result in sensitivity drifting. Also, the thermal properties are susceptible to the temperature variation. So we can conclude that the variation of temperature not only has a direct effect on the sensor performance, but also indirectly affects the sensitivity through the thermal properties of the working fluids. The exponents of the working fluid thermal properties for the sensor sensitivity in this table show that the sensor performance can be more affected by thermal capacity, thermal expansion coefficient, and thermal diffusivity than thermal conductivity. According to the analysis in the 2D model, we propose two normalized sensitivity functions with and without the consideration of the impact of the thermal properties at different ambient temperatures based on the curve fitting as shown in this slide. These two functions figure out the compensation ratio for the sensitivity of the sensor and are used to develop two different ambient temperature compensation algorithms, namely compensation 1 and compensation 2, shown here. The fabrication process of the tin sensor chip mainly consists of 5 steps, as shown in this process flow. The process starts with the growing of the electrical isolation layer on a silicon substrate, including the low-stress silicon nitride and silicon dioxide. Platinum film is then deposited on the electrical isolation layer and patterned by litho process. In step 3, an additional silicon dioxide layer is formed as the mask for the subsequent etching process and to protect the patterned platinum film. Cavity boundaries are defined by etching the silicon dioxide and silicon nitride layers in step 4. In the final step, deep reactive ion etching is used to define the deep trench first, and the releasing of bottom silicon substrate is realized through thin difluoride isotopic etching. The fabricated sensor chip was then packaged in a PCB and assembled on a rotation platform with the wireless connection between a laptop and an Arduino MCU, which realized by a Wi-Fi router. In order to realize the ambient temperature adjustment, the whole experimental setup is put in an oven with a temperature sensor for real-time temperature monitoring. Both the ambient temperature and the sensor output can be recorded by Arduino MCU in the experimental testing. Here, the two developed different temperature compensation algorithms are adopted in the open-source Arduino MCU for experimental testing. The response of the tin sensor at different ambient temperatures before and after compensation 1 are shown and compared in this PPT slide. We can see that the temperature compensated tin sensor under compensation 1, considering the impact of the working fluid's thermal properties, shows an excellent temperature-insensitive output with the maximum variation of 1.88%, compared with the maximum variation of 36.28% revealed by the uncompensated counterpart. So, the drifting of the sensor output due to the temperature variation is effectively improved by the compensation method. In addition, the compensated results with compensation 1 and compensation 2 are shown in the left figure here for comparison, and the variations of the sensor output at different ambient temperature can be seen from the right figure here. The results show that the stability of the sensor outputs can be greatly improved by compensation 1 compared with compensation 2 and the uncompensated results. So it is necessary to consider the impact from the working fluid's thermal properties when developing the compensation method for the tin sensor. Also, we introduce the temperature drift of sensitivity TDS, which is defined as the change of sensor sensitivity per unit temperature change to evaluate the compensation results. Different from the maximum variation, TDS indicates the variation of the sensitivity with the ambient temperature. The experimental results show that TDS of the tin sensor was suppressed from 14,732 ppm per degree C to 591 ppm per degree C by compensation 1 and to 8,098 ppm per degree C by compensation 2. This result further validates that the developed compensation 1 is better compared with the others shown in this table. In this work, we developed an integrated temperature compensation algorithm for the tin sensor based on theoretical and experimental analysis. The theoretical study with the extended 2D model indicates that the sensor sensitivity is susceptible to the thermal properties of the working fluids, which can be affected by the ambient temperature. The developed temperature compensation method was used to successfully overcome the problems of inconsistent sensor output to show a good sensitivity of 0.6434 mV per degree per second, with the maximum variation of 1.88% and TDS of 591 ppm per degree C, which is much better than the other results. That's all for my presentation. I'm very thankful to these institutes making great contributions to our project. Thank you.